Right, so I'm doing this is the assignment for 1.2.4 reading and interrogating the text. So let me start by reading it first. Electric field of a point charge. We'll begin to put the definition of the electric field to full use in the next chapter. For now, to develop the ideas, we'll determine the electric field of a single point charge Q. Figure 22.24a, so it's this one right here. So shows charge Q in a point in space at which we would like to know the electric field. So this is the source charge that creates the electric field, and we're using this point charge right here to test out the electric field strength, or also the direction at this point. So yeah, so to do so, we'll use a second charge Q as a probe of the electric field. For the moment, assume both charges are positive. The force on Q prime, which is repulsive and directed straight away from Q, is given by Coulomb law. So since both of these are positive, we learned that they will repel each other. So the force exerted on this Q prime is going to be in this direction since they repel each other. And based on Coulomb's law, which is electrostatic force equals K Q1 Q2 over R squared. So we learned in the last section that when dealing with electric field, we can replace the K with 1 over 4 pi epsilon 0. And so that becomes this. And then we have the two charges, which is Q and Q prime over R squared, which is this distance right here. Yeah, away from Q is the direction. It's customary to use 1 over 4 pi epsilon rather than K for the field calculations. Yep, that's what we talked about. Equation 22.5, to find the electric field in terms of the force on a probe charge. Thus, the electric field at this point is... So we know that the electric field strength is force on Q prime, which is the point charge used to test the electric field strength at that point, and over the charge of the point charge. So like we can, since we're setting up, since we're making over the charge doesn't matter anymore because it cancels out right here. So let me rewrite it real quick. Because you have Q prime over R squared, and over, so this comes right here. So these two cancels. So the charge of the point charge used to test the electric field strength doesn't matter. Like the charge doesn't matter since they cancels out. And this Q is the charge of the source. So yeah. Note the expression for the electric field is similar to Coulomb's law. To distinguish the two, remember the Coulomb's law has a product of two charges in the numerator. To describe the force between two charges, the electric field has a single charge in the numerator. It is the field of a charge. Yep. So yeah. So right here we have two charges. They can that positive and negative, so they can be different. But right here, since the charge of the test charge, the charge of the point charge are canceled out, we're only left with the source charge Q. So we only have one charge right now. And in this case, it's positive since it's written here. If we calculate the field at a sufficient number of points in space, we can draw a field diagram such as the one shown in figure 22.25. Notice that the field vectors all point straight away from charge Q. Also notice how quickly the arrows decrease in length due to the inverse square dependence on r. Okay, so what we did for this part is calculating the electric field strength at that one point in space. So like at this point in space, and that force is this the magnet. It's a vector, so it has the magnitude and the direction. But if we do that, the textbook's saying that if we do that, if we imagine like if we drag around this q prime like around in space, we would get like a lot of arrows pointing in different directions at different length. So that's how we get the electric field. That's how we get the electric field diagram. So essentially, these are all q primes, except at like different locations. It's also saying that um, um, since the based on Coulomb's law, the the force decreases as the distance gets it's as the distance gets bigger, since it's r squared on the bottom. So you can tell like this length is a lot shorter than this, since it's a lot farther. Also, I want to mention that the direction is formed by the test charge and the source charge. So like when you connect the two, like the direction exerted on the test charge is like forms a straight line. Yeah, keep these three important points in mind when using field diagrams. The diagram is just a representative sample of electric field vectors. The field exists at all the other points. A well-drawn diagram can tell you fairly well what the field would be like at a neighboring point. Yep, so it's yeah, it's just saying that the diagram is showing a few points. It should be like everywhere, since like a field, it doesn't really have like dots. It should be like everywhere, but like this gives us like a general idea of like approximately like what the field strength would look like at like certain points. The arrow indicates the direction and the strength of the electric field at the point to which it is attached, that is, at the point where the tail of the vector is placed. In this chapter, we indicate the point at which the electric field is measured with a dot. The length of any vector is significant only relative to the length of other vectors. Yeah, so it's saying that this arrow is representing the direction and the magnitude that this point charge right here, that is experiencing from the source charge. So at this point, the electric field the electric field strength is the length of this arrow, and the direction is the direction of the arrow. And the second part saying that the length of any vector is significant only relative to the length of other vectors. So since like arrows doesn't really have a unit, we're just comparing like the lengths of different arrows. So like this one's obviously going to be a lot shorter than this one. So like the strength is also going to be a lot weaker. 3. Although we have to draw a vector across the page from one point to another, an electric field vector is not a spatial quantity. It does not stretch from one point to another. Each vector represents the electric field at one point in space. Yeah, so it's saying that so it's saying that although we're drawing an arrow, it's really only showing like this point right here is what this point is experiencing. It's like it's not spread across the space. It's just like this arrow is only representative of this point right here that the tail is attached to. Yeah. So that's it for my video. Thank you for watching.